So let's do problem number 66 from chapter 4 together. Um, so I'm actually just going to talk through the solutions that I posted on MyCrystal, um, just to kind of like, be explicit about my thought process. When I'm reading a question, like what am I looking for? What am I thinking about? All that good stuff. So question number 66. We're asked what mass of silver chloride can be prepared by mixing 100 milliliters of zero point 0.2 silver nitrate with 100 milliliters of 0.15 molar calcium chloride. And then the second question, or second part of this question, is calculate the concentrations of each ion in solution after the precipitation reaction is complete. So the first thing that I want to point out here is that, again, there's two questions. So we have the mass of silver chloride and then calculating the concentrations of everything. On any quiz or test that I give you, I will split this up into part A and part B. I think when it's like mushed together in one question like this, it's a little hard to kind of see what's going on. It's easy to get lost. So we have question A, question B. We'll do question A first, mass of silver chloride that can be produced. So we're going to do some stoichiometry, and I know that in order to do stoichiometry, I need a chemical equation. In this case, I have written the full formula equation. You could work from a net ionic here. I don't think that in this case it like really matters that much. I don't know that it's really going to give you any advantage working from a net ionic. So I just worked from the formula equation. So here's silver nitrate, calcium chloride. We know that silver chloride is going to be the precipitate. We're kind of told that in the problem, right? What mass of silver chloride can be produced? So we're already told that, but you could imagine that you'd have to go to your blue sheet, figure out that silver chloride is your precipitate, and then of course we've got calcium nitrate. All right, this is a limiting reactant problem because we're given volume and concentration of each reactant. So 100 milliliters of 0.2 molar silver nitrate, 100 milliliters of 0.15 molar calcium chloride. So the way that I'm going to handle that in my calculation is I'm going to go over to silver chloride with each of those, right? So we're going to do moles of silver nitrate to silver chloride and moles of calcium chloride to silver chloride. And then whichever one's smaller, we're going to take that number. So here's my calculations. The one in black is for silver nitrate, so that goes to silver chloride. And the one in blue is for calcium chloride, that goes to silver chloride. Okay, I can make 0.02 moles of silver chloride from the silver nitrate and 0.03 moles of silver chloride from the calcium chloride. So that must mean that silver nitrate is my limiting reactant, AgNO3, because this number is smaller, right? 0.02 is smaller than 0.03. So this is the actual number of moles of AgCl that I'm making. Okay, so one thing I want to point out here is this is the same thing that we did in 10th grade chemistry, right? Even down here converting to, didn't mean to do that. Converting to grams of AgCl, right? This is 10th grade chemistry stuff. We did limiting reactants. We did moles to grams conversions. If you are hung up on this part, let me know ASAP, right? As soon as possible, let me know. Because all this other stuff isn't gonna really work if we can't comfortably get through this type of calculation. All right, so that's like the first part of the question. Second part of the question, calculating concentration of ions in solution after the reaction. All right, so let's think about what was in solution initially before the reaction. So I'm going to separate all of this stuff into its ions. So I've got Ag plus, NO3 minus, Ca2 plus, and Cl minus, right? So imagine if you took this equation and you wrote it out like in a total ionic equation, right, where we ionize all of our aqueous stuff. That's our ions that could be in solution, right? So ions that could be in solution, Ag, NO3, Ca, and Cl. But here's the important part. Up here, I identified AgNO3 as being the limiting reactant because it is the reactant that gave me the smaller amount of product here. So this is limiting. That means that it was used completely. And specifically, it means that all the Ag was precipitated. right? Because that is like the ion out of that that's precipitating. NO3 is a spectator. NO3 will never precipitate. But this silver right here, this Ag, it precipitated as AgCl. And because AgNO3 was limiting, that means that we precipitated all of that silver. All of that silver came out of solution. So there's no silver still in solution here, right? It's the limiting reactant. Okay, let's hop over to the next slide and let's put some numbers to all this stuff. Okay, so we have identified silver as being the limiting reactant, which means that all of it precipitated. There's none left in solution. Ca2 plus and NO3 didn't precipitate. They're spectators. So their moles before the reaction, meaning aqueous moles before the reaction, and their aqueous moles after the reaction are the same, right? It didn't go through any phase change. It didn't go through precipitation, so we don't have to worry about that. So we get moles of NO3 from the moles of AgNO3. It's a 1-to-1, so we got 0.02 moles of NO3 initially. So we're doing 0.02 over the total volume, right? 200 milliliters, 100 plus 100. That gives us that concentration. And then for calcium, same idea. We have 0.03 moles of calcium chloride, or excuse me, 0.015 moles of calcium chloride. And so it's 1-to-1 with the calcium. So 0.015 moles of calcium over 200 milliliters, 0.075 molar, right? So we don't have to worry about any of these precipitating because they're spectators. So spectators' moles before and after are the same. The chloride is the one that takes a little bit more work to figure out because some chloride did precipitate, but not all of it because it wasn't limiting. Only the silver was limiting. So how do we figure out how much chloride is left over? Well, we do what we initially had, right? So that comes from the CaCl2. I actually showed that on the bottom here. 0.015 moles of CaCl2. There are 2 chlorides per 1 CaCl2, so that's 0.03 moles of Cl minus. So this is what we had initially, minus what precipitated, right? And here I say this is what is used. I actually don't like that phrasing. I'm going to say what was precipitated. I think that makes more sense. And then we come over here to get what's left over. We just do what we had initially minus what precipitated. Oh, I did use that phrasing up here. So initial minus precipitated gives us what remained, right? And so in this case, it's 0.01 molar. We put it over 200 milliliters, and we get that concentration. Okay, so one of the things we talked about in class was to answer this question, like how much is left over. We can always do, so we'll do moles remain equals moles initial. This is before the reaction minus moles precipitated. Right? You're always doing this work. Right? This is the math that we're doing. If it's a spectator, the moles precipitated is 0. So that's how we get that the moles remaining is the same as the moles initial. That's where this idea comes from here for the calcium and the nitrate. If it's limiting, your moles initial and your moles precipitated are the same. So you would have some number minus itself, which gives you 0, which again is how we got the idea that silver has 0 molar concentration in solution. And then if it's something like chloride, where only some of it precipitates, then you do your moles initial minus moles precipitated, and you get what's left over. So in this case, 0.01 molar. Okay? This is a very, down the middle of the plate, just not easy problem, but a very straightforward example of the solution stoichiometry stuff. So if you're struggling with these steps, either the stoichiometry part in the beginning or the calculating moles concentration left over here, again, let me know so we can figure that out, because it really only gets it really only gets more challenging from here. Speaking of, we're going to go ahead. We're going to talk about number 70, which is just a little bit more involved, a little bit more challenging. So let's head over to the next slide and do that. All right, so number 70. So kind of the same idea, right? We're still doing solution stoichiometry. But you'll notice that this question is, like it's a little bit different than number 66. And that's kind of the theme, right? Like we're sort of picking up these skills. We're picking up these like specific assets that we use to solve problems. And we got to learn to apply them to other situations, right? Okay, so we're given 1.5 grams of a mixture of sodium nitrate and sodium chloride. Now, we don't know like which is which in there, right? We don't know if it's a 50-50. We don't know like sort of what the ratio is, but 1.5 grams total. We're going to put that in 100 milliliters of water. It's going to dissolve, and then we're going to add excess 0.5 molar silver nitrate. We're going to see a white solid precipitate. We're going to collect it, filter it out, dry it, and measure it. And it's going to have a mass of 0.641 grams. All right. So I picked this problem for a couple of reasons. One, we get this idea of an excess reactant. And I've gotten a lot of questions about like, what does that mean if it's an excess reactant? When we say we add excess of something, what we mean is we're adding so much that it has to make the other stuff the limiting reactant, right? You're adding so much that there's no way that you've got enough of the other thing to completely react with it. Okay, so in this case, we're told there's a precipitation reaction. That precipitation reaction is AgCl coming out. That's the only thing that can precipitate, right? None of these sodiums will precipitate. We know the nitrate doesn't precipitate. It's got to be sodium chloride, it's got to be silver chloride coming out of that solution. So when we say we add excess silver nitrate, what we're saying is we're going to add so much that all of this chloride is going to precipitate in the form of AgCl. That's what excess means. The other reason I picked this question is actually because this is a little bit more relevant to a test question that I have ready for us. It talks about collecting, drying, and measuring the solid. So remember, this is happening in aqueous solution, which means when we filter something out, right? If we were to filter out this precipitate, it's going to be wet. It's going to have water on it. So we got to dry it and get rid of that water before we measure it so that we get like an accurate mass of 0.641 grams, right? So kind of we actually don't do a filtration lab because filtration's pretty annoying to do in a lab setting. But I wanted to emphasize that idea. All right, let's start with question A. So if we're looking at Magic School Bus, kind of like what's left in solution, what species are here? By species, we mean ions. So we've got the sodium, right? That comes from the sodium nitrate and the sodium chloride. We got the nitrate. That comes from the sodium nitrate and the silver nitrate. We got some silver because we added excess silver. Notice what's missing from this list, though. What's not here? I did not put chloride on this list. Why? It's not a mistake. There's no chloride in solution. Chloride was limiting. We're not told directly that chloride is limiting, but we're told that we added excess silver nitrate. That means that chloride had to be limiting. That means that we added so much silver nitrate that we definitely precipitated all that chloride. Okay? So it is not a mistake that chloride's not on the list. Chloride's not in solution. It all precipitated. Now, I did have a couple people email me and say, well, water also ionizes into H plus and OH minus. Shouldn't those be on the list? Yes, I do think that's an oversight. However, in the context of this question, that's not a huge deal for us. So let's leave it to the ionic species that are present here. All right, we have our net ionic written. So this is one where I think the net ionic kind of getting rid of like the sodiums and like all that stuff, I think just like simplifies this a little bit more, right? Because we got that kind of mixture thing. So there's our precipitate. It's a 1-to-1-to-1, already balanced. We're good to go. Let's hop over here and let's use this mass of precipitate. So we're told that 0.641 grams of precipitate. So we can figure out how many moles of AgCl that is, right? I just divide by the molar mass of AgCl. And then I can figure out how many moles of Ag that is, right? I'm just using this ratio from the equation here. It's a 1-to-1, but, we're still doing stoichiometry. So we have 0.0044725 moles of silver and 0.0044725 moles of chloride. We know that this chloride had to come from the sodium chloride. That is the only source. Wow, I totally did not mean to do that. Okay. There we go. We know that sodium chloride, or that the chloride had to come from sodium chloride. Okay. That is the only source of chloride up here. Sodium chloride, right? Nothing else had chloride in it. So we're going to use that amount of chloride to work backwards to figure out how many moles of sodium chloride we had. And it's a 1-to-1. There is 1 Cl for 1 every NaCl. So again, doesn't really change the number, but we're still doing stoichiometry. Okay, so now we have 0.0044725 moles of NaCl. I'm going to turn that into grams because in the third question, in part C, I'm asked for the mass percent. So I want to be in grams here, right? So we go to mass percent. Now, we haven't done a mass percent problem in the context of solution stoichiometry, but you did one in the lab, right? You did a mass percent for our carbonates lab. And if you remember, it was percent CO2 is mass of CO2 over mass of the sample times 100. Right? So we're going to take that idea, right? We're taking the bones of that calculation and we're going to apply that to this solution stoichiometry. We're asked for the mass percent of sodium chloride. So it's going to be mass of sodium chloride over the mass of the sample. That's going to give us our percent of NaCl. And look, I even use the same little notation down here. Percent NaCl, mass of NaCl, mass of the mixture, times 100, because we're making a percent. Right? See how we're taking pieces of what we've done and like applying them to problems that are like not exactly the same, but similar? That's a theme for this year. That's our theme. All right. So we got our mass of NaCl by working backwards from the precipitate, moles of chloride in the precipitate, mass of chloride in the precipitate, moles of chloride in NaCl, mass of NaCl, right? So now we're here. 0.261373 grams of NaCl. That's the result of our calculation. I'm just bringing that number down. And then this 1.5, that's given to us in the problem. It's over here. That was the first line of the problem, 1.5 grams, right? So we do that division, multiply by 100. We figured out that that mixture that we had initially was 17.4% NaCl. And if I asked, like, well, what was the percent of sodium nitrate? You would just do 100 minus that, right? So you could even get to the other thing if you wanted to. Okay, so similar to the last problem, we got a little bit of like excess reactant, limiting reactant. This mass percent stuff here, right? We did this in the lab. We haven't seen this show up in solution stoichiometry. I love this, like working backwards from the precipitate and like getting back to your initial stuff. I think that's a great little sequence there. That's a hint for the quiz. Okay. So that is question number 70. So 66 and 70, a little bit of homework help. Hopefully that was helpful. Send me a question if you got it. Check out the playlist. I'm going to put some other videos over here to help us get ready for the quiz and the test.